Hello. Today we'd like to discuss the binomial probability distribution. This is the first of our discrete distributions. A random variable is a quantitative or numerical variable that's measured or observed in an experiment. So in our dice lab, we rolled and the certain number of times a sum was obtained was the random variable x that we were concerned with. A probability distribution is an assignment of probabilities to the values that can occur for that random variable. And our notation will be x, capital X for the random variable, such that we have a certain type of distribution described by two variables. In our dice and probability lab, for each outcome, the sums 2 through 12, we obtain the probability for each outcome by dividing the total ways to obtain each sum out of the possible 36 outcomes. This was our probability distribution, so we could write out what the probability is for 2, 3, 4, 5, 6, all the way through 12. Let's consider the 3 coin flips example. So if we tossed a coin 3 times, what would our sample space look like? What is the probability that you flip exactly 2 tails? And what's the probability that you flip exactly 1? Heads. Here's what our sample space looks like. In our sample space, we write with brackets. And we have 3 heads. We have heads, tails, heads, heads, tails, tails, heads, heads, tails, 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 and so on. So we have all these different combinations. It turns out we have 8 altogether. So the probability that you flip exactly 2 tails, when we come down this list, here's 1, and 2, and 3. So that would be 3 out of 8. And what's the probability you get exactly 1 heads? So this would be this one here, this one here, 2, and 3. So that would be 3 out of 8 as well. So we could do this for a simple sample space of only 8 outcomes. But the problem occurs is when we want to find out what's the probability of getting exactly 4 successes out of 100 experiments. So in that case, we would not be able to write out the 100 different combinations. So we'd like to use the binomial probability distribution. This has some nice rules and some nice math behind it if you have 3 specific conditions. So our conditions are there can only be 2 outcomes. Like our coin flip, we had heads or tails, that's it. The outcomes have to be independent. So the second flip cannot depend on the first. And then we have to have a fixed number of trials. And here's just an entire page just of notation. So our binomial probability distribution is represented by the random variable x, such that we have a binomial probability distribution. And it's represented by n, the number of trials, and p, which is our probability of success for any trial. And so the really important values that we need to pull out of each question when we're looking at a binomial probability distribution is what is our random variable? What is the success? N is the number of independent trials. That's our total number of experiments. P is the probability of success for any trial, and Q is the probability of any failure for any trial. And these will all make sense as we walk through a concrete example. So suppose we have a basketball player with a 74% free throw percentage. So we're saying that they make 74% of their free throw shots. If the player shoots 25 shots, what's the probability of them making exactly 16 shots? So here, if we wanted to write out all the possibilities of his 25 shots, we would have to say hit, miss, 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 miss 24 times. Hit, hit, miss, 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 miss 23 times. And we'd have to write out all those possible combinations. And we don't want to do that. So we're going to make life easy and use some math. And we have some special calls on our calculator that'll help us get through this type of question. So the first thing we want to do is check for conditions for binomial. So we have a specific percentage, 74%. We have a fixed number of trials, which is 25. The player either makes the shot or they don't, so there are only 2 outcomes. And the second shot does not depend on the first, so we do have an independent situation. So in this example, X would be the number of shots made. N is our number of trials, which is 25. P is our success rate, which is 0.74. We're going to change our percentage there to a decimal. And our failure rate then, since there's only two outcomes, would be 1 minus 0.7, which is 0.26. So in other words, if he makes it 74% of the time, 26% of the time he does not. So how do we find this? So here's what we want to do. We want to break out our TI calculator. The first thing you want to do is on your calculator, and let me see. Oh, I don't have an extra calculator pulled up right this minute. So what you want to do is hit the second button on the top right of your calculator, and then it will say VARs. Second VARs is your distribution menu, and that will bring you to this first screen. Once you get to the distribution menu, you're going to scroll down to 0 for binom PDF. So that's binomial probability distribution function. This is an older calculator. This is a TI-83 that I'm showing you the screen for. In this type of calculator, you would put in N, comma, P, and then the X that you're looking for here is 16 because we want to know the probability of him making exactly 16 shots. And so once you put those three values in separated by commas, you will end up with 0.0896. And so we're saying about 9% of the time they'll make exactly 16 shots. If you have a TI-84, it will specifically ask you for the number N, it will ask you for the success rate, and it will ask you for X, the number of shots that you're looking for, which will be 16. So yours will be a little bit more intuitive rather than the parentheses and commas. The new question we want to ask is, what is the probability that out of 25 shots, a person with a 74% free throw percentage makes at most 16 shots? So at most means that they make either 1 or 2 or 3 or 4 or 5 all the way up to 16. So we're looking at the probability of each of those. So I could in my calculator run binomial PDF for 1, 2, 3, 4 all the way up to 16 and add those all together. But our calculator has a nice shortcut. So we're going to go second VARs again and take us to that distribution menu again. This time scroll down to A for binom CDF. And that CDF is the cumulative distribution function. So that will add up all of the probabilities from 1 to 16. And if we do that, we end up with 0.179. So 17.9% of the time, our free throw shooter will hit either 1, 2, 3, 4, 5, all the way up to 16 shots. So that's the at most case. And what if we have the at least case? So suppose the question is, what is the probability that out of 25 shots, a person with a 74% free throw shooter percentage makes at least 16 shots? Now, at least is very different from at most. At least means that they make 16 or 17 or 18 all the way through 25. Our calculator only adds up to a value. So if we already know, if we can find the probability of at most 15, subtract that from 1, and we'll end up with everything left. So we have 1 minus binom CDF, where our X is 15. So if you look down here on our calculator, we have 25, 0.74 is our P, and in this case, our X will be 15. That would be 0.0893. And that's the probability that we have at most 15 shots made. But we want the probability that the rest of the events happen, 16, 17, 18, all the way through 25. So what we want to do is we want to use our complement rule from probability and say 1 minus 0.08934, and we get 0.91066. So as a general rule, if you have the at least situation, you want to take 1 minus the binomial cumulative distribution function of 1 less than the number that you're looking for. So if it says at least 16, you want to take 1 minus the cumulative probability for x equal to 15. So I hope that helps clear things up just a bit. If you still have questions, feel free to email or get in touch when you can. Thanks.